Hey guys, it's Mr. Sheeline here. This is going to be the lecture video notes covering the Unit 6.4 material, which is concerned with percent yield. So up to this point, we have been working with stoichiometry, where we were changing, we'll say like substance A into substance B. So it'd be like the mass of substance A, and we changed it to particles of substance B, or moles of substance A to particles of B, whatever it had to be, we did that there. Then we did BCA charts where we determined what was our limiting reactant, our excess reactant, and we then also looked at how much of the product would be produced, X, Y, and Z, all that good stuff. So now we're going to be getting into kind of the analysis portion of all of that work. Okay, this is really what this analysis portion is. So percent yield, looking at its description here. So the percent yield is the amount of product actually produced from a reaction compared to the amount of product that you expect. So what we have been practicing is pretty much this portion right here, is the amount that we expect. Okay, we've been specifically working with just calculations on pen and paper. Okay, now in real life, it always doesn't end up exactly what we have on our pen and paper here, okay? Especially if we don't keep our measurements exactly, spot on like they should be. So percent yield is where we're going to take the actual measured amount of whatever the product is, or whatever has been left over, and we're going to divide it by, divided by the theoretical, the calculated mass, and then multiplying it by 100 to see how close we were. So obviously the closer to 100%, the better that our answer is. The further away from 100%, the huge gaps that we have in what we calculated versus what we were able to produce in the lab. Okay. So that's what percent yield is. It's just to see how close your actual lab measurements were to what you calculated. And what you calculated is what we've been practicing with BCA charts specifically. So this one really is just getting, or this one getting straight to it. So, and actually before I do that, let's just make sure we understand. So remember, the actual is, this is given or recorded in the lab. Okay, so the actual is either given to you or it's recorded in the lab. Theoretical is what we calculated. So this is the amount of product you mathematically calculate. Okay, so again, this is what we've been practicing. This is what you get from your lab or what's been given. Okay, so let's take a look at two examples here. And we only have these two examples in the notes, and this is pretty much what we're looking at. So example one is pretty much just going to be, it's going to be more or less somewhere where everything's been given to you, and we just have to see what it is. So we're given, we're going to be given the limiting reactant, we're going to be given an actual measured amount, and we just have to really compare here, okay? Whereas in number two, it's like number two down here, we're like starting from scratch. So we have to complete a BCA chart first. We have to convert a particular material or particular substance into its mass, and then using that mass, we then will divide that mass with what we actually got and see how close we were in that. So let's take a look at number one. So what is the percent yield of water if 25.6 grams of CH4 is combusted according to the following reaction and 45.0 grams of water is produced? Okay, so there's a whole lot going on in this question that we have to be able to identify. Okay, so it's asking, what is the percent yield of water if 25.6 grams of CH4 is combusted according to the reaction and 45 grams of water is produced. So what do any of these numbers mean? Well, let's first identify what the question is. So what we're going to be answering, and I'm actually going to keep using these highlighters. So what's being asked and what we have to answer is this. What's the percent yield of water? What's the percent yield of our water? How much does our calculated amount compare to what we actually measured? Okay, and this is what's been given. So we've got this 25.6 grams of CH4. So what does that 25.6 grams of CH4 have to do with anything? Well, it's going to react here with O2, which is going to result in us having CO2 and H2O as our products. So this guy right here, this is what it's saying is that more or less this is our limiting reactant. It's just to say that we start here, how much of this are we going to end up with? So starting here, how much are we ending here? So in other words, what are we doing here? We're just doing stoich. This is just simple stoichiometry, and then we're going to use the percent yield equation in order to solve for this. Okay, so that's what that is. So then what's this 45 grams of water? So, and it says here, you know, combusted according to the reaction, and then it says here that 45 grams of water is produced. So this right here is our actual. This is our actual mass of water. Okay, so this 45 grams is our actual mass of water. So we will be saving this to work in here at the end. What we first need to do is to see just how much, theoretically, you know, what we're going to calculate, how much water do we expect to be produced. So we're going to convert mass of substance A, which is going to be CH4, into substance B, specifically mass of substance B, which is going to be H2O. So let's just get going. So it'll be 25.6 grams of CH4. We're going to convert that to moles of CH4. And in CH4, there's 16.0 grams to every 1 mole of CH4. Okay, so that cancels, bang, bang. Okay, so now I'm left here with one mole of CH4. And now I've got to convert moles of CH4 into moles of water. So I'm going to have moles of my old stuff down here, moles of my new stuff, which is going to be H2O up here. And looking at the coefficients, there's 1 mole of CH4 to 2 moles of H2O. And then all I've got to do is just convert moles of H2O, because these all cancel out. I've got to convert moles of H2O into mass of H2O. So in 1 mole of H2O, there is 18 grams, 18.0 grams of H2O. So that cancels because of that, and then I'm left with grams of water. So multiply across the top, multiply across the bottom, divide top from bottom, and then I'm going to get this. And here we got to keep sig figs. So I should get 57.6 grams of H2O. So this guy right here, this is now my theoretical. Okay, this right here is my theoretical mass. It's what we just calculated using math, just using simple algebra. That is what we just calculated, okay, my theoretical mass. So this is the actual, this is what we actually measured out. Here is what we expect to see. This is what we should expect to find at the end of the reaction. So obviously, clearly, there's a difference between these. So what we want to do is to see just how much of a difference there is. So we're going to use the equation up there. So percent yield is equal to the actual, so 45.0 grams of H2O over 57.6 grams of H2O. Okay, and then that's going to be multiplied by 100. Okay, and roughly speaking, 45 divided by 57.6, and I'm going to get somewhere around about 78.1%. Okay, so in this case, we are quite a ways off. So this says that you know what we just calculated with the 78.1% is to say that we were roughly 3/4, you know, the actual was roughly about 3/4 of what we expected to see, which is not particularly a good place to be. So there is something happening, whether temperature was off, and this is something we don't have to, that you have to determine. It's just, you know, talking about how we get such a large discrepancy. but it's possible that, it's very, very possible that maybe we didn't have enough oxygen. Maybe the area was oxygen deprived. It's also possible that maybe our apparatus that we were using to collect water, maybe there's still water collected somewhere that we weren't seeing. Maybe the temperature ultimately changed how much water we were able to collect. Maybe the time that it took in order to grab all the water, maybe we left it out too long and we lost water that way. Whatever it is, it's not good that we have a percent yield this different. Because remember, the ideal is to be as close to 100 as possible if you want to make sure, or if you totally expect to get this amount. Like if you want this amount, you want this number as close to 100 as possible. Okay. Now, just understand though, like when we're practicing this, I mean, it's not like there's any magical way that you can make this any closer. It is what it is. Okay. This is what we actually got. This is what you calculated. There's nothing you can do to get it any closer to 100 other than having to restart your experiment and to, you know, fix anything that needs fixing. Okay. So that's what that's how we calculate percent yield in this case. So let's take a look at where we basically start from scratch. So we're going to have to more or less come up with this right here. Or more or less, actually, it's quite different. We're asked to find the percent yield in a reaction between 53.8 grams of aluminum chloride and 73.5 grams of iron 2 sulfate if 51.6 grams of aluminum sulfate is recovered. Okay, so let's break this down because this is asking a whole lot. And we got to do a whole lot in this. So first it's asking what is the percent yield in a reaction between 53.8 grams of aluminum chloride. So it's, what is the percent yield in the reaction? Okay. And it's really just one question. I should be a bit more specific. So here, this is our question. And then here is our actual. This is our actual mass. So what's being asked here is we need to find out what the percent yield is specifically of just aluminum sulfate. Okay, the question is asking, okay, when you combine this with this, so this the amount of this stuff plus this stuff, we actually found this, but what was the theoretical? Okay, what did we expect to see? And once we have what we expect to see, how much does our expectation meet with what we actually found? So we're going to make a BCA chart here, okay, and we're going to just basically just do this. And I put this in a bad spot, but B and then the C and then the A. Okay. So the first thing I've got to do is I've got to realize that I'm starting off with mass of this stuff. So I'm starting off with 73.5 grams of the iron sulfate. And I'm starting off with 53.8 grams of the aluminum chloride. So I've got to change this into moles, and I've got to change this into moles. So let's just start with this one since it's the first one that came up. So we've got to change 53.8 grams of aluminum chloride into moles of aluminum chloride. So in 1 mole of aluminum chloride, we have roughly 133.5 grams of aluminum chloride, which is roughly going to give us, so 53.8 divided by 133.5. Roughly speaking, it's going to give us about 0.40299, we'll just say 6. Okay, that's moles of aluminum chloride. Okay, now let's change the, and actually we'll put this guy up here because that's where, or specifically here, so there's 0.402996. Then we're going to change this guy, so 73.5, man, I am not leaving myself with a whole lot of room, but we got room, we can work on the back, that's fine. So we got to convert this to moles, so in 1 mole of iron 2 sulfate, there's roughly about 151.9 grams of iron sulfate. And once I put that together, so 73.5 divided by 151.9, I should have something like this, 0.483870 we'll just say actually 7.1. We'll just say that. Okay, and that's moles. Moles of FeSO4. Okay, and then I'm going to write this guy up here, so that's going to be 0.483871. Okay, and remember on the before line, this is 0, that's 0. And now we can start figuring out, you know, who's got the lower, who's going to be my limiting reactant. So I'm going to divide these by their coefficients. So the aluminum chloride has a coefficient of 2. Iron sulfate has a coefficient of 3. So I'm going to get 0.402996 divided by 2. It's going to give me roughly about 0.201498. And then here, 0.483871 divided by 3. It's going to roughly give me about 0.16129. Okay. Now, clearly this guy is smaller, my iron sulfate here, so that means that my limiting reactant is going to be iron sulfate. Okay, that's my limiting reactant. So the iron sulfate's going to run out before we can, you know, completely use up the aluminum chloride. Okay. And so we're also going to be using this guy right here. We're going to be using this as our multiplier. So we're going to multiply now the, we're going to be multiplying the coefficients with this number here. So 3 times 0.16129, and then it'll be 2 times 0.16129, then it'll be 1 times 0.16129, and then 3 times 0.6129, or 0.16129. Okay. So what we should get here is we should just get back to our normal number here, which is 0.483871, because this is our limiting reactant. And then here, got to calculate this one, 0.16129 times 2, which is going to be 0.32258. And over here, it's just going to be 0.16129. Then here it's going to be 0.483871. Okay. And then I just see how many moles are going to be left. So here it's going to be 0 moles. So we run out of the iron sulfate. Here, for my aluminum chloride, 0.402996 minus 0.32258. It's going to give me about 0.080416 moles. Here, it's just going to be 0.16129 moles. Here, it's going to be 0.483871 moles. Okay, so now we got to go back to the ultimate question. And the ultimate question is, what is our percent yield of specifically aluminum sulfate? So we're going to see aluminum sulfate here. We've got to find out just how many, or just how far off our actual measurement was from the theoretical that we have just now found. So this is a number of moles of aluminum sulfate that we now have to, we've got to convert that into, we've got to convert this into mass. So we're going to put this down here, 0.16129 moles. And I got to scrunch all this in. Actually, I'm gonna do this on the back. I'm gonna do this on the back of the paper here. So it's going to be 0.16129 moles of aluminum sulfate. Okay. Ooh, sorry. And then we are converting from moles to mass, so we're going to use some molar mass. So in 1 mole of aluminum sulfate, we have roughly about 342.3 grams of aluminum sulfate, which, and here we're going to keep sig figs, is going to be roughly about 55. Actually, I better double check that. 0.16129 multiplied by 342.3. Okay, which is going to give me roughly about 55.2 grams of aluminum sulfate. Okay, so here, this is my theoretical. This is my theoretical mass. This is what we expect to see at the end of our lab. Sorry. So now this is where we're then going to use the percent yield to see how far off we were. So percent yield is going to be the actual divided by the theoretical. So we'll say A over T. Okay. Actual over the theoretical times 100. Okay. Which is going to, when we plug it in here, it's going to turn into 51.6 grams of aluminum sulfate divided by 55.2 grams of aluminum sulfate. It'll be all multiplied by 100 afterwards. So it'll be 51.6 divided by, not multiplied by, divided by 55.2 times 100. It's going to give me my percent yield, or it's going to give me a percent yield of roughly about 93.5%. And there I have my final answer, and the answer that we are looking for, which is the percent yield of this reaction. Okay. So again, what does this 93.5% tell us? Well, it tells us that we were roughly about 7%, more like 6.5% away from meeting the actual, or sorry, meeting the calculated amount of aluminum sulfate that we should have seen after this. Better way of saying this. This right here, our measured, is roughly about 7% away from being what we expected to see in the theoretical. Okay, so we're pretty close. Okay, and that's pretty close, which is pretty good. Okay, still a ways away from where we would say for sure that we did everything that we possibly could in order to produce the best results, but still, like, way better than 78%, I can tell you that, which is awesome. Okay, so anyway, that is how we calculate percent yield. That's two ways that we can calculate percent yield. First way, again, is going to be we're given everything for the most part, and all we have to do is use stoich in order to see what the theoretical mass is. Okay, but then there is this form where we are given here the mass of our two reactants, and we have to figure out how much, we have to predict how much of the product will be made depending upon the limiting reactant of our material here. Okay, so that is what we expect to see and what we expect to have. So that is the video there, guys. If you still have any questions for me, let me know. Make sure you get a hold of me. We're winding down. This is the last material for Unit 6. So we're just going to be practicing this further until the unit test. So make sure you get a hold of me. Make sure that you are completing all your materials. That if you have anything that's missing, remember, you can turn that in before we take the unit test. So make sure if you've got anything missing that you're continually working on it, and you're getting it to me either on Google Classroom or you're handing it in person, whatever it is. So anyway, that's it for this video, guys. If you have any questions, let me know. If not, I'll see you in the next one.